Hi, everyone. I'm Erik Brynjolfsson, and this is the Stanford Digital Economy Lab Lunch Seminar. Today's speaker is Max Tegmark, joining us. Well, he's from MIT, but he's joining us from New Zealand today. He's a professor of physics at MIT, and his research is focused on precision cosmology, combining both theoretical work with new measurements and parameters. Today, he's going to be talking about the physics of intelligence, and he's been doing a lot of work on machine learning and AI more broadly, and using physics-based techniques to better understand biological and artificial intelligence. He's also the co-founder of the Future of Life Institute and has thought about some of the broader implications of these technologies. So we encourage your questions during the seminar. The way to do that is through the little Q&A function you see down at the bottom of Zoom there. So just click on that and type your questions in. And I will occasionally interrupt Max and pass on your questions to him. We're also going to try and save about 10 or 15 minutes at the end for general discussion, so you can also have a discussion during that part. So Max, welcome. It's great to see you. And please tell us about extracting machine learned knowledge.
Wonderful. Thank you so much for that kind intro, Erik. As Erik alluded to here, in the last 6 years, I've shifted my MIT research group from physics to machine learning because it's just so much fun. And I think one of the things we physicists can contribute to machine learning is that we have an even higher bar than engineers do about what we mean by actually understanding something. And raising that bar to understand things even more deeply, I think can be really valuable for making systems that you really trust because you understand what they're doing. Now, if you take a neural network like Erik Brynjolfsson's brain, and you watch it in action, and it looks at all the data that comes in through its eyes and ears, and it sees some patterns and it has an insight. Now there's some knowledge in Erik's brain about the economy or about something else. We know that we can actually extract that knowledge from Erik's brain. We can be like, Erik, explain this to us in a pedagogical way. And then what he will do is he'll take this squishy, complicated insight that he doesn't understand how his brain even encodes, and he will put it in a symbolic representation, English, or maybe math, and explain it to you. So he can transfer the knowledge to you. And this is, of course, why it's so great to talk to Erik, because we can learn important things from him. And this is why we can also trust Erik's models, because he can explain them to us in a rigorous way. And I want to talk about how we can try to do the same thing with neural networks that are not in Erik's head or your head, but artificial neural networks. How can we, once they have learned something, and by golly, machine learning can learn a lot, how can we extract that knowledge into a form that makes us trust better what the thing is doing, that can be copied and written up in more efficient ways, et cetera, et cetera. One of the reasons I switched to doing AI research is because there's just so many opportunities. Obviously, things are moving so fast in terms of AI progress. Did this slide just change, Erik?
Yes, it did.
Background? Great. Yep. So just think about it. This is a state of the art of robotics 6 years ago. This is extra humiliating for me because one of these guys is actually the MIT robot, the DARPA challenge. If we fast forward, it looks like this. So the momentum in the field of artificial intelligence is just really, really palpably high. Not long ago, we didn't have self-driving cars. Now we have self-flying rockets that can land themselves with artificial intelligence. Not long ago, we couldn't do good face recognition. And now we can not only do that, but we can simulate Erik's face saying things he never said. Not long ago, we couldn't save lives with AI, and now we have AI systems that are as good as the best humans at diagnosing prostate cancer, lung cancer, eye diseases, and various other things. For 50 years, we couldn't solve the protein folding problem. Then Google DeepMind's AlphaFold just blew away all the biologists and crushed the problem. You can see here how it's taking a genetic sequence of amino acids and figuring out the 3D shape that the protons fold into, in really good agreement with X-ray crystallography measurements. Not long ago, machines couldn't beat humans in the board game of Go. And of course, now DeepMind's AlphaZero, then Mu0, not only crushes human players at Go and also at chess, but more interestingly, it crushes AI researchers like myself, people who had spent decades handcrafting algorithms, which are now made obsolete by machine learning. And if you play around with Google Palm and you ask it this question, hey, Trevor has wanted to see the mountain with all the heads on it for a long time, so he finally drove out to see it. What's the name of the state that's directly east of the state that Trevor is in? If you haven't seen this, before, take 5 seconds to see, can you answer this question? And then reflect on the fact that not only can Google Palm answer it, but it was able to learn to answer this from an incredibly dumb training task, just reading ginormous amounts of text and trying to predict the next letter or word from what it had read so far. That was it. Much like you take a human baby and you let it watch what mommy and daddy and others say for a long time, and all of a sudden it actually learns to speak and understand a lot of things. And the number of neurons or parameters in this model is actually sort of roughly the geometric mean between a mouse and a human. So it's maybe not.
So, wow, is there really that big a difference between a mouse and a human? That's a quite. I didn't realize it was that many orders of magnitude.
It is pretty shocking how many neurons we have. Yeah, given how smart mice are. Yeah.
Yeah, mice can do a lot.
So, a lot of reasons to be excited about the progress, of course, of AI, and a lot of reasons to think it's going to get a lot better. But there are obviously challenges as well that come with having something super powerful. The reason that the US has now announced in the past week or two that this massive set of new restrictions on China on Chinese AI is because it's beginning to sink in Washington that powerful AI is coming, and a lot of people who think that whoever gets it first is gonna rule the world. Then there are also a lot of people who think that if we build super powerful AI like this to rule the world, that we're probably all going to die. Stuart Russell is probably the AI professor who's been most eloquent and going on and expressing this for many, many years. So people have been thinking a lot in recent years about how we can make sure that this ever greater power of AI really makes humanity flourish like never before, cure our diseases and make everybody healthy and wealthy and so on, rather than just become the end of humanity as we know it. And the three key strategies I feel are all really central to make sure to steer the use of AI towards this awesome future that we could have and away from the bad one. One of them is what Stuart Russell likes to talk about: just get away from giving totally open-ended and maybe poorly specified goals to machines so that they go out and accomplish really well things that weren't what we wanted. And there's a lot of nice nerdy technical work in that vein. Another front I think is really interesting is multi-scale alignment. Andrew Critch up at Berkeley likes to talk a lot about that. In the AI safety community, we talk a lot about the alignment problem of aligning the goals of an AI to the goals of its owner. But the point here is that's of course not enough. We also want to align the goals of the humans that own the AI with the goals that are going to make society flourish. This is why we invented a legal system, for example, to make people incentives to do things that were actually in the greater good and not the opposite. This is why we invented gossip and other forms of more soft feedback than jail sentences to make sure that what people do is actually in the greater good, that they are honest, that they're not moochers and so on. And but there are and this is of course the core thing about economics as well. So Erik has done a lot of work on how you can create economic incentives so that when people just do what's best for their own wallet, they will actually do what's best for humanity. So there's a lot of work to be done there. And none of those two is what I'm focusing on this talk, because I'm going to focus on the third one. How can we take these ever more powerful AI systems, which are often in the form of black boxes where we don't understand much about their inner workings, much like a human brain, and actually get the knowledge out of them so that we can actually trust these systems, not because the salesperson said, oh, trust this is great, but because we understand it. There's a lot of amazing progress, for example, in formal verification techniques, such that once you can extract the knowledge, turn it into Python code or mathematical formulas or whatever, we can do these automated things to check that it actually is what we want. So that's the focus, opening up the black box, all right? Just a little plug, if you are listening to this and you're applying for grad school soon, or applying for postdoc, or applying for a faculty job, I just want to give a shout out. We have a new center at MIT that's been going for a while now. It's basically AI meets physics. It's called iFi. I think you would love it here if you're interested in the topic of my talk. We have a lot going on, and a key part of it is very much trying to get deeper understandings, new tools for understanding better what's happening in AI. We have also with the Future Life Institute that Erik mentioned, launched this AI existential safety community for people who like to think about these big questions. You can become a member of it. We have 8 postdocs so far, hiring another 8, and you can also be a member of it just as a way of being part of our community events, webinars. We have an internal grants program where you can get funding for little things. Go to Future Life Institute or Google for Future Life AI Existential Safety Community, or email me if you're interested in this. And finally, my own group is very focused at MIT on this business that we're going to talk about today, extracting learned knowledge from black boxes. So if you're interested in working with me, you know who to email. So what I'm going to do now is to give you a few examples of recent papers we've written on this very theme of getting knowledge out of a black box. Please feel free to chime in with questions for clarifications whenever. And I hope this stirs up a fun discussion we can all have as well, starting in about half an hour. So let's start with a very simple example where you have a giant Excel spreadsheet, which I suspect you economists, Erik, have lots of. Yep. And you're just interested in predicting the last column from the other columns. If you run a linear regression, then that's a very easy computation to do, and it's very easy to interpret what you learn because it's just a matrix. But more generally, what if it's some more complicated function of the other columns? That's the problem of symbolic regression. So we did this NeurIPS paper called Pareto Optimal Symbolic Regression Exploiting Graph Modularity, and that's such a mouthful. Let's unpack it, this title, one piece at a time. So symbolic regression, what's that? It's predicting the last column from the other columns and looking for a symbolic formula that's as good an approximation as possible. It doesn't have to be linear. And this is unfortunately believed to be an NP-hard problem, just because the number of formulas of length n grows exponentially with n. In fact, Johannes Kepler here spent 4 years working on this problem for Mars data that you see plotted in the lower left until he solved it. And it's like, oh, this is an ellipse, and revolutionized astronomy. I'm going to show you our machine learning system that automatically discovered that formula in about 1 hour. What's this graph modularity all about? Well, you can think of any function as a computational graph, like I've drawn in the middle of the slide here, where you take numbers and you combine them together in pairs or whatnot with different operations. And I'm calling a function modular if a function of many variables can be decomposed into functions of fewer variables. Here you see an example of what looks like a function of 3 variables, but it's secretly just a couple of functions of 2 variables that are combined. And a key insight we had for this paper is that if you train a neural network, just a black box neural network, to just accurately approximate the function on the left of 3 variables, for example, you have no idea how it works, just by studying the black box and looking at certain algebraic relations between the gradient of this function, you can discover any modularity that it has, no matter how complicated. So was quite shocking to me when we realized this. So for example, so step 1, you train a neural network. Step 2, you'll discover the middle representation, that you can write it as 2 functions of 2 variables, but you don't know what they are. And then you can repeat that and try to build a divide and conquer system where after you discovered all the modularities, eventually the pieces are simple enough that you try to discover what they are, and then you put it together. And the way that algorithm of ours works in practice is very much in Julius Caesar's divide and conquer spirit. You have a spreadsheet, in this case, with 4 columns, predict the last from the first. Then it trains a neural network to fit this, and with some nonlinear function. And then it's like, oh, I discovered some patterns, some structure, some modularity, and it can split this into 2 problems with fewer columns. And over and over and over again, it does this. As a concrete example, suppose, yeah.
And Max, is you sort of like that, especially the last step of then trying to figure out what the formula is it sort of at some point kind of a brute force testing a bunch of different ideas, or is there something more different than that? And I think you want somebody that a lot of like physicists do this as well, that they'll kind of try a number of different formulas to see which one might work.
That's right. So there are, once you get down to very few fewer variables, so there's this thing known as the curse of dimensionality that says generally figuring out what the function is gets exponentially harder when you have more variables. So it's a big win that you reduce the number of variables. Once you have very few variables, if it's a function of 1 variable, for example, you can just make a plot of the curve. That gives you a lot of insights. If nothing else, you can do it just a spline fit, and which will be super accurate. But very often we try automatically various other techniques like brute force, try a bunch of formulas. You can do 1 billion per second or something. In increasing complexity, we also you can see if it's a polynomial or some other simple function classes. So to illustrate this with an example, let's take the mystery formula that we don't tell the computer to be Newton's law of gravitation in the upper left corner there with 9 variables. So you make a 10 column spreadsheet. First, it does some automatic dimensional analysis for the physicists who might be listening to this. So you reduce it to 7 variables. And then it trains a neural network to fit this 7 variable function. And it discovers, oh goodness, there's some pattern. There's a modularity here. It only depends on C and D through the difference between the 2. So it can combine them into 1. So basically you replace the C column and the D column by C minus D, and then you do it over again. And then it discovers, oh, now the new thing only depends on E and F through their difference. And then this even simpler formula, it discovers another thing, that A is just multiplied by some function of B and G and H. So it gradually decomposes it into smaller and smaller pieces until it's able to just figure out exactly what each piece is, put it all together, and kaboom. I'll show you in a sec some benchmarks for how well it works. But first, I have to tell you what this other mouthful is. What's Pareto optimal? So as an economist or a scientist in general, you of course are not just interested in something that's accurate. You would also, if you are given the choice of 2 formulas that are equally accurate, you go with a simpler one. So we quantify here both the inaccuracy of each formula and the complexity of it. and plot each formula on a two-dimensional plane like this. And given our preference for simplicity, Occam's razor, we're interested particularly in convex corners in this plot that are both very simple and very accurate. So you see that there are two of them here. In the lower right corner, you see this one formula, which you see has very good accuracy. And the reason for that is that's the kinetic energy of, according to Einstein, for a moving particle. It discovered the formula that we had put into it. But there's another convex corner that it also discovered, which is mv squared over 2. So for those of you who remember your high school physics, this is the approximation that human beings, including Isaac Newton, thought was the true formula for many, many years. And the one that's still so useful as an approximation that we teach in high school. So I thought it was kind of interesting that we can actually codify Occam's razor to the point where the machine will give us the approximations that we humans feel are useful. Whereas I think you've never learned the formula in the upper right corner in a school, because that approximation is neither uniquely simple or complex or accurate.
So I guess one implication, when you're starting off, you were sort of describing finding the formula, but in some sense, there may be several formulas that are worth looking at, depending on how precise you need to get. It may be that you're willing to have a little bit of inaccuracy for a much simpler formula, like in this case.
That's right. We've gotten much more humble also in physics over the years, gotten away from this hubristic thing that we thought we had exactly the right formula, to realizing that all the formulas that I teach at MIT are wrong at some level. They're approximations to something else that we haven't discovered yet. And so it's very fair to have this sort of criteria. If you have a formula where you get much more out of it than you put in, very simple formula that explains a lot, that's what we mean by useful. And I think similarly in economics, you would never believe that any of your formulas is completely exact in your model for demand as a function of price or something like that. But that doesn't prevent you from finding sometimes really useful approximations. Our measure of simplicity, we picked a compromise between Occam's razor, which is so vague that it doesn't even have a formula with it and you can't code it up, and the super rigorous Solomonoff complexity, which is provably NP hard to compute, by having a cookbook prescription for calculating how many bits you need to store the formula written down here, which is actually quite fast to evaluate in practice. And let me show you how it works. So tested, we took the Feynman lectures on physics, the books that actually got me to want to become a physicist. And also we took the most famous or complicated formulas out of there, the 100, and then another bunch of complicated formulas from some grad textbooks, etc., and elsewhere. And then we made these spreadsheets, and then we unleashed we also took some probability distributions, and just gave it the points to see if it could find formulas for that, and unleashed this package on it. And the state of the art used to be Schmidt and Lipson's famous genetic programming package, which got 71% of those Feynman equations. Our system gets 100%. The harder ones, it got 15, we got 90%. Those other modular complicated equations got 42, we got 100%, etc. And what was also really cool to me was that putting in this Occam's razor thing, where you reward simplicity, actually made this system between 100 and 1,000 times more robust towards noise. So I think Occam's razor and rewarding simplicity, as I'll come back to, is actually really a key strategy for learning what's really going on with a data set.
So Max, just to make sure I'm understanding what you did, you took those equations and then you generated data from them. And then in some cases, you even added a little bit of noise to the data, so it wouldn't give the exact number from the formula, and it still was able to come back and find the formula. Is that right?
That's exactly right. And we kept adding 10 times more noise and 10 times more noise over and over until it failed. So that's what those robustnesses are showing in that table, that typically we could add about 100 or 1,000 times more noise until it broke if we used Occam's razor. That's right. And the 3-word summary of this project is pip install AI Feynman, because that's all you need to type on your laptop if you want to actually play with this yourself. So without getting too into the weeds, I want to highlight just the key theme here. So this was an example where there was a black box and it learned things in some complicated way, but when we never tried to understand what was actually happening inside the black box. But we said, well, clearly there's knowledge in there. It's so accurate. It must have discovered whatever structure there is. And then we developed some external techniques, sort of neuroscience on computers, to figure out what it had learned. Like, oh, it discovered that this is modular, like this, this, and this. However, there's another kind of strategy you can do where you try to plug in Occam's razor and encourage the neural network itself to do things within itself as simply as possible. Machine learners have known this for many years. It's called regularization. You can try to penalize how many weights you use, how big they are, or you put dropout. There's all sorts of different techniques which try to starve the network or make it do the problem with less resources. And it's well known that that often makes it more likely that it'll do something smart. One example that we worked on of this type, so I'm going to go over just very briefly, is so suppose I just show you a video of something, and your task is to just predict the future of the video. Then, you know, if you're a human being, you'll be like, well, clearly the palm trees I shouldn't pay attention to. They're not even moving. The only interesting thing is the X and Y coordinate of this moving rocket. So you just extract those two variables from all of the many, many thousands of numbers that define the pixel colors. And then you can try to do now symbolic regression on X and Y as a function of time and see if you can figure out the pattern. But how do we humans know that we're supposed to pick out the X and Y coordinates rather than the color of the sun or the shape of the rocket or whatever? We wanted to see, could that be learned? And could it be learned in such a general way that even if you distorted the video with a weird lens like this, it would still figure out that it should use the undistorted X and Y coordinates to pay attention to? So we built a neural network architecture where there were 3 neural networks. One that takes the, say, 20,000 numbers that define the image and map it into a low dimensional space shown in green, maybe 5 dimensions, maybe 2 dimensions. A second neural network that then tries to go from that latent space back to the reconstruct the image. So those two together will be what's called an autoencoder in machine learning. And then a third neural network that just tries to predict the future in this reduced latent space. And this failed epically to give anything interesting until we started bringing in Occam's razor again to encourage it to come up with the simplest way of doing this. So here I was kind of inspired by physics. This guy with the burly hair, right? He said that a space is simple if it's not, the simpler it is, the less curved it is. And he gave a formula for what it means that a space is curved. And if you take a mapping like this from some space representing the past into some new space representing the next state, that defines that mapping, it will define a curvature. And you can use Einstein's formula. And I thought, why don't we just make it come up with the least curved evolution model, basically. And we were able to further simplify this to numerically accelerate it, but that was the basic idea. And skipping over all the details, at the end of the day, we're able to show it all kind of videos with distorting lenses or not. And in every case, it actually figured out how to undistort them and use the X and Y coordinates that we would use. And it even discovered the exact equations of motion of the rocket, even when it was something nonlinear like the quartic oscillator. So this simplicity business, I think, is really quite powerful.
Max, can I?
Yeah.
There's a couple of questions that I think are possibly related. That before you go on to the next thing, that maybe I could ask you.
Yeah.
So one of the attendees is asking. He says his statistician colleagues forbid him from using symbolic regression because it's combinatorially large, huge size, and search space, so that parameters are difficult to measure without a precise understanding of what the degrees of freedom might be. So it's impossible to compare the goodness of fit between two alternatives. How do you address that issue? And the other question, which might be related, is what is the loss function for symbolic regression?
Perfect. So for the first one, so which degrees of freedom should we pay attention to? That's in fact the whole point of this project. To see, can the computer automatically discover which are the degrees of freedom that are useful for predicting the future? We actually call this paper pre-regression because it's the thing you have to do prior to regression. Decide out of all this stuff, which degrees of freedom should you pay attention to? So I think that's a super interesting question that came there. And then what's the loss function for symbolic regression? Very good question as well. So we did there are two things, not one thing, that we care about. And there's the inaccuracy. That's like the traditional loss function. How big are the errors that your formula makes when predicting the data? But then there is also this other thing, the complexity. We would like to keep them both small, and there is always going to be, like in any multi-objective optimization, where there are two things, a trade-off curve, a Pareto frontier that where you can choose where you want to be along it. That what the code will actually spit out is all the ones that are on all the formulas it finds that are on this Pareto frontier. So moving along, so I alluded to the idea that regularizing something is something that's helpful for it to have smart insights, and we saw some examples of that here. I call it intelligence through starvation because it reminds me a lot of what's been happening on Earth throughout biological evolution. If you have an abundance of resources, if it's not so Malthusian in economics terms, you have no real reason to be super efficient with what you do. Whereas if it's very much, if you're very resource limited and you might starve to death, you have a very strong incentive to figure out a smarter way to make the computation that uses less watts. And that incentive we see is exactly the incentive that we want to give our neural networks also. We don't want to starve a human or some organism that's evolving so much that the whole species goes extinct, obviously. Then it's nothing very intelligent that's going to emerge. But if it's too easy, there's also not much incentive for getting smarter. It's the competitive play when there is competitive pressure, you have an incentive to do things, to see the patterns in the data and exploit them through cleverness that you really want to aim for. And AlphaZero, AlphaGo, all of those successes where intelligence has emerged from competitive self-play are a lot like Darwinian evolution, if you think about it, right? Where you really give strong incentives for doing things smarter. So let me show you a very recent couple of papers we did on that are very related to this. So here we asked a complementary question about how to get the knowledge out, rather than just having a black box and studying afterwards what patterns it might have found. We decided to look inside the black box directly and see what is it actually doing. Can we see if it learns some representations, and we can see the dynamics by which it learns how to represent things cleverly. We were inspired by this fascinating paper by Althea Power et al. She and her colleagues at OpenAI discovered this really weird thing called grokking, which many of you have heard of, where you train a neural network for a long time, and it very quickly gets good at 100% accuracy basically on the training data, but it still doesn't get it, in the sense that if you show it some other data that you've held back and hasn't seen, it completely sucks. So it's basically just memorized the data. It's just all overfitting, no insights gained. But then she discovered with her colleagues that if you train for another, you train 1,000 times as long, kaboom, all of a sudden, aha, eureka. Now it starts to do well on the test set, even though you just kept training on the data that had an overfit. So we decided to build some toy models to see if we can reproduce this effect, understand what's happening inside the system.
So just back on this chart, just to make sure. So the green line is out of sample.
Yes,
it's new data. So that's what val means.
That's validation, exactly. So you suppose you have you're training it to do some task, and you have 100,000 examples. You train it on 90,000 examples, and you show how accurately it does on them with a red curve. Right. And the green curve is how well it does on the remaining 10,000 that you didn't show it.
Right.
And you will only, obviously, it's only gotten any useful insights when it generalizes from the data that you showed it to the data that didn't show it. You didn't show it. So it's only after over 10 to the 5 steps that it's actually getting it. But it's quite intriguing that, you know, after it does this dumb thing of just overfitting, after 300 steps.
And it's hard to see on this chart, but if you look down around 10 squared, it was actually, it got a little worse on the validation data as you gave it more data. It kind of overfit. Right?
Yeah. So it's really interesting. So we looked at this a bunch, and then we eventually ended up discovering some stuff we got very excited about, where it's almost, I think of it as like there's a crystallization that happens inside of the neural network. I'll show you what I mean by this. So as a toy task, we decided to see if the neural network could just learn a group operation, multiplication or something like that. So we would give it as input images of symbols, say, that have nothing to do with the meaning of the symbols. And the task was to apply this group operation and output the image of the result. So for example, let's look at addition modulo 59. You show it a photo of 12 and a photo of 50, and it's supposed to output a photo of 3, because 50 plus 12 is 62, modulo 59 is 3. And we put in this simple architecture where first it has to learn some black box called the encoder, where it takes each image and maps it into a point, a geometric point in a space, which we interpret as all the components in the matrix. And then we multiply the two matrices, and then we train another neural network that takes this new matrix and turns it into an image. Okay, so let me just show you what actually happens. When you look inside at how the encoder actually represents the pictures of these numbers, for a while it's a mess, and then kaboom, eureka, it had some sort of insight. It realized that if it can represent all the photos of images by putting them all in a circle, it can do this task much better. Now, as a human, of course, this is sort of natural, because modular addition is exactly like adding up hours on the clock. This goes from 1 o'clock around to 12 o'clock, and you add 5 or whatever. The old-fashioned non-digital clocks, we actually draw the times as a circle, because we have realized that's sort of the clever, natural way of thinking about them. But we were quite struck by how you can see this very literally inside the computer, that, oh, there's a representation that's formed, and it's discovered the representation. And you can see it's precisely when it discovers this circle representation that the test loss suddenly plummets. That's when it is able to generalize all of a sudden. So in other words, when it puts them in this order, that even though you may never ever trained it maybe on the example 8 plus 5, that wasn't in your test set, if you make like a big group multiplication table, 59 by 59, there's like almost 3,600 answers you would have to learn. But even if you give it much less than 3,600 examples to train on, like 200 or 300 or whatever, or 500, there aren't that many parameters where these go in the circle. It's just an X and a Y coordinate, for each number. That's just less than 120. And then the representation itself basically makes the correct way of doing the calculation just sort of pop out automatically. Don't worry too much about the math details of this. The idea is very simple. If you represent your knowledge, your concepts in a geometrically clever way, then you've already done a lot of the computational work just by virtue of having the clever representation.
So Max, I can see how this representation is super helpful. Can you say a little bit more about how you get to it? Does it sort of randomly try once and find, or is there some kind of smoothness that if you're almost near the representation, then you start getting better answers? That's not so obvious to me, but like, how does it start? It looks like right there as it's kind of getting there. Is there some benefit to being almost a circle, but not a circle, that it can go down a gradient?
Exactly, there is. Although precisely there is, and that's why it's able to discover it. But interestingly, sometimes depending on how you regularize it and your learning rate and these various parameters of the training, sometimes it learns and sometimes it fails. So there's actually like a phase diagram of learning, just like water can be a liquid or a solid or a gas. We find that the learning has 4 phases, depending on how much data you have and your system for training it. So in this case that I showed you, we got to what you would call comprehension. It gets it. It learns to generalize. That's what we want with machine learning. There's this other phase called confusion, where it never learns anything. If you take a 5-year-old and you try to get them to figure out string theory by showing them a few books, you come back a year later, they're still not going to know string theory. And then there is the overfitting, where it just memorizes all the data. So it's like a really poor student who just memorizes the textbook but hasn't understood anything. They can get 100% on the exam, but they're not going to get into grad school. And then there's the 4th regime, the grokking phase, where there's this very delayed aha experience. And we were able to tune which of those happen. This is a lot like when you try to make a crystal, depending on the temperature, pressure, and so on. Either you're going to make the crystal or you're not. And to leave time for a lot of discussion, let me just step back from all the math here and tell you a little bit about how I think about it and what I think it means. I think it very much comes back to this idea of intelligence through starvation again, except here it's a bit like economics, and it's a 2-player game. You remember we had an encoder that figures out how you represent your stuff. And then there's a decoder also that tries to provide answers to the questions you ask it. And what we found generally was that if the decoder is much, much smarter than the encoder, you don't really learn anything interesting. You never get the good representations. It's kind of like if you have a baby and every time they go blah, 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 you're so smart as a parent, you always give them the milk. You understand that they wanted milk or whatever. They don't have an incentive now to pronounce things better. Whereas if you have the decoder being too dumb, so it can never answer questions correctly, no matter how cleverly the encoder encodes, there's no incentive for the encoder to learn anything, and you stay forever in the confusion phase instead of in that overfitting phase that you get if the decoder is too smart. And the magic happens. The real learning happens when you're in this Goldilocks zone, where the decoder is not too dumb, but also not too smart. So that there is an incentive for the encoder trying to make the representations more clever. And then it will. And I think this is something we see a lot in Darwinian evolution again, that if you have to really fight for resources, you're afraid of starving to death, but it's still possible to get by most of the time. that's when you really have an incentive to do things cleverly. I'm really excited about the general discussion. So I'm gonna just cut to the chase here with a little summary. After just giving you a 60-second example that I also like, well, we also applied this to black holes, just for fun to see if you have in general relativity, if you can take some solution that someone made and find an even simpler one, in the spirit of getting the knowledge out. So Carl Schwarzschild, when he discovered black holes in 2015, the conclusion was you just die at the event horizon. Because if you look at these complicated formulas without worrying at all about what they even mean, you see that there are these fractions where you divide by r minus 2m, and 2m is the radius of the event horizon. So when you're at if the event horizon, r minus 2m is 0, you division by 0, you get infinity. That doesn't sound good for your health, does it? But then 17 years later, the Swedish guy Gullstrand and this Frenchman Panlevé discovered actually you can change coordinates and see that nothing special happens at the event horizon, and you actually don't die until much later. We tried some of these ideas as well that I mentioned here, of rewarding simplicity, and our neural network was able to actually discover this coordinate transformation and this famous new way of doing black holes. So I just wanted to showcase this to illustrate that discovering simplicity automatically is something I think is not just helpful for generally making AI more trustworthy and robust, but also something that can be really, really useful for science.
Okay.
So I'm just going to close my slides and just summarize in words what I've said here. So I think that this idea of getting the knowledge out of neural networks is both very valuable. It's good for science, and it's also good for the future of humanity, because it gives us more reasons to trust the machines that we build by actually understanding what they're doing. But it's not just that it's useful. I've also made the point that it's not hopeless either. You know, I showed you a whole bunch of examples of where we're actually able to make progress on this. And what they all have in common is that the simplicity in the neural networks is created or discovered not by people, but by machines themselves. So there are other machine learning strategies you can use actually to encourage learning clever representations, encourage simplicity. And also there are techniques, automated techniques you can make that will actually discover the simplicity and extract it out in ways that we humans can understand. So I think I feel quite optimistic about the future of this direction of extracting learned knowledge. Thank you.
Thank you, Max. That's amazing. It's really exciting work you're doing and the potential for it. We have a number of questions. Let me ask one of them. One attendee is asking, grokking looks useful if there's an event horizon to determine the more useful process. If grokking is not always useful, how do you prevent the neural network from over-grokking? Or let me do a variant of that question. In your book, The Mathematical Universe, you described how amazing it was that there are often these simple equations that describe what's going on, but especially in economics, it's often that there is no simpler. It's just very inherently chaotic and difficult. So are we confident that a large percentage of our data sets have some underlying simpler formula in them, or is it sometimes that you really do need 30 billion parameters to describe what's going on?
That's a very, very deep question. I try to be humble about and acknowledge that I don't know the answer to. But I am quite confident that there are a lot of additional insights and patterns left to be discovered that are plenty simple enough, for us to find. We could have had this conversation in the recent past, and then after that, all sorts of new formulas were discovered. Then I certainly don't think we're at the end of science. Second source of optimism is, though, that, for this to be useful, it doesn't have to be understood necessarily. It can be useful even if it's too complicated for us to understand, as long as we can make our machines understand it in some formally verifiable way. Like if you have some new control system that's controlling your fusion reactor, like DeepMind came out with a while back, right? You would really feel a lot better if there's a mathematical proof that it's never going to cause this fusion reactor to explode. And even if the proof is so long that it's only verifiable by a computer, you'd still probably feel better about having that thing in your backyard than if there was no proof, right? And as we move towards artificial general intelligence that can outsmart us humans at all tasks, frankly, the only way I'm going to trust that something way smarter than us is going to treat us well is if I can prove it, because then I know no matter how smart it is, it cannot do the impossible.
Great. And speaking of these more complicated, so if it's a simple formula like an ellipse or something, then humans likely would find it. Maybe the machine would as well. If it gets a little more complicated, maybe we're going to see some machines find them that we wouldn't have otherwise found. How does this work for very complicated formulas, or is there sort of a combinatorial explosion that it can't get too complicated before you can't decompose it and find the different pieces?
My guess is that virtually all of the impressive results we've seen in machine learning, including those language models like the Google Palm example, actually correspond to it having learned some clever representation. We just haven't figured out, what it is yet. So if you look in large language models, for example, it's been well known for many years that there is geometry in the word embeddings. You go the direction from the word man to the word woman and some 500-dimensional space is more or less the same vector as if you go from the word king to the word queen, for example, right? So that's very much like the trivial example I showed you with a modular addition. Yeah. And I suspect that the reason that Google Palm was able to answer these questions was because it had learned to represent words and concepts also in some clever geometric way, which let it generalize like this. And we just haven't these simple figured out how to get that knowledge out.
And not just like man, woman, king, queen, but also maybe some higher level, more complicated things that you learn from reading Wikipedia and learning history or something.
For sure, yeah. And so but it might still be possible to think of this entirely as a geometry problem, where it's discovered some sort of very complicated sort of crystal structure or how all the concepts fit together, and that's what's enabling it to generalize. It's kind of like if you play a Sudoku or you just sometimes fill in the blanks just from the relations to all the other things. And if you put all those numbers on the clock face, right, it's pretty clear how just putting them in that geometric representation lets you solve problems like what time is it 4 hours after 3 o'clock, even if you hadn't seen it just from the representation. And my guess is that large language models and perhaps most of the things we see machine learning do today that's really clever is doing this. It's just that we haven't figured out yet how to get the representations out.
So there's two things. One is, then the machine learning figuring out some representation allows it to generalize and solve problems. You started the talk with how it could explain to us. Those may be related, but they're not necessarily the same thing. One of the questions is how does this promote explainability and perhaps reduce bias? And I guess to elaborate on that, suppose the machine learns a very complicated formula and then it tries to explain it to me. And I'm like, I have no idea what you're saying. There's a saying I saw on Twitter, so it's like, explain it to me like I'm a 5-year-old. Could it have like different layers and say, you know what, I'm not going to explain Einstein's formula, but I'm just going to explain the simpler one that we teach in high school, or some like way of making it comprehensible to us less generally intelligent entities.
Yeah, absolutely. That's possible. You know, the cool thing about so for example, if you watch a really impressive chess game played by AlphaZero, right? I would not be able to come up with the moves myself, but I can verify that they were valid and they won the game. Yeah, that's a lot easier. It's exactly the same with a mathematical proof. I might not be able to come up with a proof myself. Yes, but I could check step by step that it's a valid proof. So this is, you know, a mathematical theorem prover is a very easy piece of code to write. Discovering the proof is super hard because you have to, in principle, explore an exponential surface space. So this kind of success, I think, is very much feasible and worth aiming for. Whenever you put AI in charge of decisions that affect human lives, or where you want great confidence, you would like to first have the AI somehow extract the knowledge out in a way that the algorithm can be written in a form where you can prove that it's gonna work. And I think a very important point here is that I think machine learning is great, neural networks are great, but they're overhyped in a certain way also, in that people conflate their ability to learn, which is really unprecedented, with their ability to compute, which is not that magical. You know, if once you have learned the knowledge, take some of those tasks like modular addition or whatnot, you know, once you've figured out what it discovered, you could write a code in C++ that did exactly the same thing. It would be even faster.
A couple of lines, yeah. Yeah,
and even, yes, fine, you know, neural networks are massively parallel, but you can do massively parallel computation in C++ also. And you could, so they do not have any magical special powers for the compute itself. Their magical powers are for the learning. And so this is kind of my vision for beneficial AI in the future. We use neural networks with their black boxes to learn the things we couldn't learn otherwise.
Yeah.
Then we extract the knowledge and we compute them in some more traditional fashion, which is amenable to formal verification and so on. And this is exactly how we use the best neural networks we have, like the one in your brain, Erik, right? We use it to learn things, figure stuff out. But then once you've figured out your model for economics and you have to apply it to a gigabyte of data, you're not going to do that in your head. You're going to program something in some computer language and have it do it. And that's
this seems like I mean, people for a long time have talked about kind of unifying or combining at least the sort of symbolic, good old-fashioned AI and neural networks, and they seem like these two distinct camps. But you're describing something that almost automatically generates the symbolic representation that then could be implemented, and then you can do some of the things we're pretty good at doing symbolically. You know, some like you said, theorem proving and logic and doing things at a high speed. And also explainability. We seem to be able to describe to each other in symbolic terms things more easily than the billions of neurons.
Exactly. So to summarize, you put it very well there. I would summarize it as saying, let's use, for safe and beneficial AI in the future, let's use machine learning to learn. But when we're actually computing, the thing that's actually going to control that fusion reactor should not be a neural network when it's in operation. That should be something else, which runs the computation using all the insights that were learned by the neural network, but it should not be the neural network.
Yeah. Well, absolutely amazing, Max. I'm so glad you're doing it and your team. I'm really excited about the potential here. I'm afraid we're out of time. So there were a number of other questions. Hopefully we can preserve some of those questions and pass them on to Max so he can learn from them as well. But I appreciate you joining us from New Zealand. This was terrific. Oh, I should ask, there are papers you alluded to there. Can we put them on our website, links to your papers, and even if you want your slides?
Absolutely. Yeah. And they're on the art. You'll find them all on the archive if you search for Tegmark. And if you had more questions you didn't get to ask here, you can email them to tegmark@mit.edu, and I'll do my best.
Great. And how long are you going to be staying down there, down under, Max? Do you have a timeline for that?
We were just, Maya and I were just discussing that last night. So hopefully I'll know tomorrow.
Okay. Well, great. Awesome seeing you. Always such a pleasure. I learned so much from you, and we all do. I really appreciate you taking the time to share those insights with us.
Thanks for having me. This was great fun.
Great. See you, Max.